Okay, good morning to everyone, and I hope you guys have had a good weekend. So, today, guys, this is the schedule. This is how the schedule will be lined up. At 7, which is like right now, I'll be having a session with the grade 10. Grade 10 maths, and we'll be doing algebraic expressions. Then at 9 a.m., which is this morning still, we'll have a grade 8 session at 9 a.m. and it will be on whole numbers. All right. Then later on in the evening, 7 p.m., I'm going to have a session with the grade 9s and it will be on whole numbers. And then at 9 p.m. this evening, I'll have a session with the grade 11s and it will be on exponents. So please, guys, take note of the schedule. All right. And I will only be going according to the schedule. So this session that I'm going to have now is for the grade 10s, the grade 10 maths learners. I'm having a session right now with them on algebraic expressions. Then I repeat again at 9 a.m. I'll have a session with the grade 8s on whole numbers. Then at 7 p.m., grade 9, I'll have a session with them on whole numbers. And then at 7 p.m. tonight, I'll have a session with the grade 11s on exponents. So this is the order of the schedule for today. The early bird catches the worm. So the grade 10s right now should be up, all right, because the schedule was posted yesterday. And I posted the schedule early yesterday so that people can have an idea already for today what will be happening. So I repeat again, 7 a.m., which is right now. Okay, it's 3 minutes past 7. I've had to reiterate the schedule. Now at 7 a.m., I'm going to have a session with the grade 10s on algebraic expressions. Then at 9 a.m., I'm going to have a session with the grade 8s, which will be on whole numbers. Then at 7 p.m., I'm going to have a session with the grade 9 on whole numbers. And then last but not least, the grade 11s. I will have a session with them later on this evening at 9 p.m. All right? And it will be on exponents. So guys, basically this is the beginning of our maths journey, us covering the term 1 maths content for next year. So all grade 10s right now should be on the live. All right, please share the live with any potential grade 10 pure maths students that are here in South Africa. Share the live with them so that they can also join in, because I will be now kicking off the first section or the first subtopic in the grade 10 pure maths syllabus. All right, I'll be kicking that off right now. Okay, and after I have done the session, I will upload the live maths session onto my YouTube channel, which is also called Maths is a Game. The YouTube channel is also called Maths is a Game. So I will post the live session that I've covered and the content that I've covered onto that page, so that if there's any learner that missed out on today's session, the pure maths session on grade 10, the grade 10 content, then they can rewatch that session on the live session that I've uploaded on, and then they can actually redo that. Okay, so that's very important. Okay, now can I ask that those people that are like rushing me to say let's start the session, please, you need not be impatient, because remember, some people are actually coming into the live for the first time, so I need to be able to reiterate what I'm saying to them so that they have an idea. So if you followed me and you're following this channel for the first time, this channel will be basically for the next few weeks. I'll be covering the content for various grades. Okay, so I'm just going to repeat it again for those who are probably joining in for the first time. 7 a.m., which is obviously 6 minutes have passed since then, I'll be doing grade 10 maths, all right, the algebraic expressions. That's the subtopic. Then at 9 a.m., I'll be doing the grade 8 maths whole numbers, okay, for South African students. Then at 7 p.m., which is later on in the evening, grade 9s, I'll be doing maths whole numbers. And then 9 p.m. later on tonight, I'll be doing grade 11 exponents. So let's dig into the session. So all grade 10s, you are welcome for the next 45 minutes. You can spend this next 45 minutes with me and we can cover the content that has to do with your syllabus for this year for grade 10 pure maths students. All right, so let's get this party started. So first and foremost, I do want to say to the grade 10s that are joining in, you did grade 9 maths this year, all right? And your grade 9 maths, all right, was very important in laying a foundation. In fact, your grade 8 and your grade 9 maths was important for laying the foundation for the maths that you will be doing in grade 10 come next year. So the whole initiative that I'm having right now is I'm actually running free maths classes on TikTok so that you guys can have the opportunity of being exposed to the syllabus for your grade 10 maths early, right? The benefit of doing that is that if you get exposed to the maths early this year, which is basically this year, late this year already, then come next year, when you start doing it in class, it will be like you are doing revision. You will not be hearing the maths for the first time, you'll be hearing it for the second time. All right, and that should actually help you in your performance. All right, I just need to make it clear to those who are actually now joining the live that I have no intention of teaching maths on the platform than for learners to actually at the end of the day attain a level 7. Nothing more, nothing less, guys. A level 7 is what basically my intention is. That is why I'm actually doing this. I'm doing it so that people can actually become very efficient, and also they need to become very good at doing the mathematics. So remember, okay, last time I was here, someone asked me a question. What advice would I have for any learner that's in grade 8, 9, 10, 11, and 12? How can they improve their results? And the only piece of advice that I have is that if you want to do well in your mathematics next year, then the first important step is you need to first and foremost start doing or covering the content that you'll be doing next year now, not when next year comes, but start doing it now. Start early. The earlier you start, the better it is for you. Then you need to couple that early start with a positive attitude. You need to believe in your heart of hearts, and you need to believe in yourself that you can actually do wonders. You can do very well in mathematics. It doesn't matter how you may have felt about maths in the past, or it doesn't matter how you might have done in maths in the past. You can actually start now having a very good and positive attitude about your maths performance. Okay, all right. And yeah, let's pick it up from there, guys. Let us start now. Okay, so let us begin. So officially, hello class of 2025 grade 10. I welcome you officially to the maths class for 2025. Now on the 16th of December, we are starting early so that next year we can just do wonders in our maths content. Okay, so let us begin. So if you can look at the schedule, it says grade 10 maths algebraic expressions. Now, in the ATP that I put up on the page, all right, you should see that it actually says the following for the grade 10 learner. All right, it says the first thing that you guys are supposed to do is you need to, as it says on the ATP, understand the real numbers. Understand that real numbers can be rational or irrational. That is the first thing. And we are supposed to first revise the number system. So guys, for the next 45 minutes, that's the only thing we are going to do. And after I have taught the content, I will then post up some exercises that you guys need to do. And after you have done those exercises, then you can actually just check with yourself if whether you have actually were able to understand the content for today. Okay. So we need to understand that real numbers can be rational or irrational. Okay. So let us revise the number system. Okay, so let us begin. All right, so guys, okay, so first and foremost, I just want to take us through the following here. I just want to say mathematics is required, okay? Mathematics is required for nearly everything you will do one day. That's the funny thing is that maths is actually required in everything that you will do one day. Some form of maths is always required in or for nearly everything you will do one day. Now, I just want to also say there is no such thing as a maths person. You may look at yourself and be like, maths is not for me. Maths is for certain people. Now, I just want to say clear out from the beginning that there is no such thing as a maths person, or when you say I am not a maths person, there's no such thing. Okay, so this is maths, guys. It's pure maths. Okay, it's not maths literacy. So this is for grade 10 learners that are doing pure maths. Okay, there's no such thing as a maths person or saying I am not a maths person. I want to say we can all do mathematics. It's very impossible to say we can all do mathematics. Everyone can do mathematics. And why is that the case? It's because it just takes what? It takes practice. Okay, we can all do maths. It takes practice. So if you practice it, then you can do it. I don't know if you've ever played a game, whether it be on the cell phone or whether it be like an actual game that you play. Usually at the beginning, whenever you play a game, it's not easy. But as you play it, the more you play it, it becomes easier, right? It becomes really, really easy. So we're going to begin by revising the real number system. Now, what do we mean by the real number system? Now, the word real obviously speaks about something that exists, something that we can actually touch, something that we can actually, that's tangible, that's there, that exists. So when we talk about real number system, we are talking about numbers in our number system that exist. Okay, we've got a family of numbers, all right, which we can divide into two. All right, so here's the thing. The real number system, okay, please take note of this symbol here. This is the symbol that we use. Is this R here. This R, that's kind of like got a double strike at the vertical end. It's like a double strike here. This here stands for real. Okay, so this is a symbol that we use to define the real number system. It's this R that has like a double vertical strike. Okay, then here it is. The real number system can be divided into two. So the first type or the first division of the real number system is we have what we call rational numbers. Okay, and this is the symbol that is used to define rational numbers. It's this Q, right? And you can see this Q is kind of like a Q. It's just like a standalone Q. So there's rational numbers, and then on the other side we have what we call irrational numbers. And look at the symbol. It's a Q, but it has an apostrophe. Okay. So we have real number systems. The real number system can be divided into rational numbers. Okay. And it can be divided into irrational numbers. The rational numbers have a symbol that is just Q, a standalone Q. Okay. And then irrational numbers have a Q, but it has an apostrophe, okay, which is very, very important. Now, if we look at the rational numbers alone, let's just forget about irrational numbers. Let's look at rational numbers. Rational numbers can further be divided into integers. Okay, so that's why we have this circle. If you look at the big circle for real numbers is represented by this very big circle. Then we can divide real numbers into rational, which is why I have a line here that divides rational into irrational numbers. Rational numbers have this symbol that we use, which is Q. And then we have irrational numbers that have this symbol that has a Q, but the Q has an apostrophe. Okay. Then if we look at the family of rational numbers can further be divided into integers. Okay, I'm very sorry about the noise here because I do stay in a street that has cars. We have rational numbers can further be divided into integers. And look at integers. The word integer, the symbol that we use for integers is this Z, but it has a double strike on the vertical diagonal line. Okay. Then we have integers, all right? We can further subdivide those into whole numbers, okay? And then whole numbers can further be subdivided into natural numbers. So whole numbers have this N symbol, but then it has an 0 at the bottom. We say the subscript of the N is 0, okay? And the natural numbers have a N symbol, which is basically N, okay? So we are going to go into and actually define what rational numbers are, what integers are, what whole numbers are, and what natural numbers are. So one step at a time, we'll actually do that, okay? Then irrational numbers, like I said, okay, are basically having this symbol that we have a Q that has an apostrophe at the top. Cool. So let's go into the definition of each of these respective numbers. So first and foremost, this symbol stands for natural numbers. So this is the symbol that we use for natural numbers. And natural numbers are what? Natural numbers are simply numbers that start at 1. Natural numbers start at 1. This is where they begin. But when they increase by 1. Up until where? Up until infinity. Now this word infinity simply means they go on forever and ever and never stop. So natural numbers, though they start at 1 and they increase by 1, they basically have no end. So up until infinity is just another way of saying to you, there is absolutely no end to, and there is no limit in how far these numbers can go. All right. So natural numbers, I repeat, have this symbol. It's just an N. It's a standalone N with a double strike across its diagonal vertical. Then we say those are numbers that start at 1, increase by 1, up until infinity. And this is just an example. This would be the set of natural numbers. 1, 2, 3, and obviously this ... indicates that there are more numbers which we basically obviously couldn't be able to fit in because there is no end and there is no limit to how far we can go with natural numbers. So remember, people, 1 is a natural number, but the number that follows 1, which is another natural number, is 2. Any number between 1 and 2 is not a natural number. So for instance, we can't say 1,5 is a natural number. Why? Because we said that natural numbers, they start at 1 and then they do what? They increase by 1. So this is the thing. This is what distinguishes one natural number from the other. They increase by 1 up until infinity. In other words, there is no end. Okay? So 1 is the first natural number, followed by 2, followed by 3, and then you know the rest, followed by 4, 5, 6, and so it goes. That is our family of natural numbers. Okay? I hope that is clear for everyone. Can I then move on to the next number that we have? The next type of family of numbers that we have. So the next family of numbers that we have are what we refer to as whole numbers. How do we distinguish between whole and natural numbers? Whole numbers also have the symbol N, which has a double sort of like strike of diagonal vertical, all right? But then the only distinction is that instead of just being a standalone N, there's an N with a 0 as a subscript, okay? In other words, the 0 is written just slightly below the n. All right. So this is a symbol that denotes whole numbers. Now, what are whole numbers? So the spelling, people, is WHOLE, because this whole means complete. Okay. So this whole means complete. It's not like the hole that's like, if you dig a hole. No, no, no. This whole means complete. So what are whole numbers or complete numbers? Simply put, whole numbers, they are numbers that start at 0. Remember what? Natural numbers, they start at 1. But whole numbers, they start at 0. And then what? What do we know about them? They increase by 1 up until infinity. So once again, whole numbers, they start at 0. This is grade 10, okay? Whole numbers start at 0. They increase by 1 up until infinity. Okay, so this is basically the set of whole numbers. Grade 10, people. This is grade 10. 0, 1, 2, 3, 4, and so it goes. Right? Remember, we said whole numbers, they start at 0, increase by 1 up until infinity. Okay, and this would be the set or the family of whole numbers. All right, 0, 1, 2, 3, 4. So unlike natural numbers, whole numbers start at 0, whilst we know that natural numbers start at 1. Whole numbers start at 0, but natural numbers start at 1. But the manner in which they increase, they both increase in the same way. They increase by 1 up until infinity. So hopefully that is clear for all of you guys. And the way to remember that whole numbers start at 0 is by seeing that symbol of whole numbers. Okay. Please check my live schedule, guys. On my TikTok page, I posted the live schedule for Monday maths. Grade 9 will only be done later on this evening. So at the moment, I'm doing grade 10. After this session, which is at 9 a.m., I'll be doing grade 8. Okay, so now I'm doing grade 10. Okay, please go onto my TikTok page. On the home page, you'll see the schedule for today for the different grades. Okay, so whole numbers, like I started 0, increase by 1 up until infinity. Hopefully we understand what the difference is between natural numbers and whole numbers, and we can see the difference between the symbols. Let's move on to the third type of number under rational numbers. We have numbers called integers. Now, what are integers? Integers are positive and negative whole numbers. I repeat, integers are positive and negative whole numbers. That's what integers are. And if we just look at an example of the family of integer numbers that we have, basically we would be talking about numbers ranging from negative infinity all the way to positive infinity. Remember, the word infinity simply means no end. So there's no end to the negative numbers. There is no end to the positive numbers. These numbers simply go on from left to right, the most negative number that you can think about to the most positive. But what we need to note is that they are positive and negative whole numbers, which means they increase and decrease by 1. So if you look at this family, we have ... which means there are numbers before this -3. That's to indicate that. Okay, then I just want to show you there's -3, but after -3, -2 follows. After -2, -1 follows, because what are we doing? We are increasing by 1. Then there's 0, 1, 2, 3, and it can go on 4, 5, 6, and so it goes. That is the family of integer numbers that we have. So integers are positive and negative whole numbers. All right. Okay. It's like we take the whole numbers, okay, which is numbers that start at 0 and go on to infinity, and then we basically extend them by introducing the negative whole numbers as well. Okay, so those are integers. Integers are simply both the positive and the negative whole numbers. So integers are positive and negative whole numbers. And here I am just showing you an example of the family of numbers that we refer as integers. I put the dot 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 here to indicate that there's more numbers before -3. Okay, I could write them down if I wanted to, but the thing is, I wouldn't have enough space to write down because there is no beginning and there is no end to our integer family, if that makes sense. So these numbers increase and decrease by 1. Okay, so something that's common about all three of these numbers, natural numbers, whole numbers, and integers, is that they increase and decrease by 1. That's what's important here. But natural numbers start at 1. Whole numbers start at 0. Integers basically include both positive and negative whole numbers, and basically they can go on forever and ever on both ends. Okay. Yeah. So Tloho, definitely, like I said, after I'm done with this live, I'll be posting this video onto my YouTube channel, which is also called Maths is a Game. So on YouTube, there's a channel there called Maths is a Game. After I'm done, I'll post up this video so that people can go and re-listen to it if they want to at their own pace, and they can basically stop, start, and take down the notes, you know, to their heart's content. But if you are here and you already have your notebook and you're taking down the notes, I hope you are, so that you can basically just refresh and recap when you do have the chance and watch the video again on YouTube. Okay, let's go on. Now guys, I've just explained natural numbers, whole numbers, and integers. And remember, these are the numbers basically that we include in our rational number family. Rational numbers include integers, which we've learned are both positive and negative whole numbers. They include whole numbers, which are numbers that start at 0 and increase by 1 up until infinity. They include natural numbers, which are numbers that start at 1 and increase by 1 up until infinity. Okay, so this basically includes the rational number family. Okay, rational numbers we'll look at the definition very shortly, and we'll look at the definition of irrational numbers. Odd numbers doesn't have a symbol. Yes, it doesn't have a symbol. Odd numbers are just odd numbers, and basically they are included in all of this. We'll talk about odd numbers very shortly. Now please take note of the following. Not all numbers are real numbers. The even root of any negative number is called non-real or imaginary number. Okay, I'm going to repeat this. Reread, this is grade 10. Not all numbers are real numbers. Okay. The even root. Now by even root, please people take note. You'll see the example. I'll show you the example just now. The even root of any negative number is called non-real. So there's a there are numbers that we refer to as non-real numbers, or in other words, we call them imaginary numbers. Okay. These are negative numbers that have an even root. So let's look at an example. If you take, for instance, the square root of -1. Guys, I'm just going to show you something. If you go to your calculator and type in the square root of -1, and then you say equal, this is what happens. Maths error. All right. Now the thing is, this maths error is to indicate that these numbers are not real numbers, but they are non-real numbers. These are all numbers that are negative numbers. They are underneath a even root. Remember, this is what we call a square root. Square root. So the square root, there would be a 2 here. This 2 is an even number. That's why I'm saying the even root of any negative number. So the square root of a negative number will give you a non-real number or an imaginary number. So we call these non-real. Okay, when we put them or punch them into our calculator, we get this maths error. All right. So this basically, the square root of -1 is non-real. Here's another non-real number. The square root of -28. Do the same thing. If you say the square root of -28, put it in your calculator. What do you get? There we go again. Maths error. Okay. Same thing. If you say the square root of -25, okay, because this is a negative number under a even root, you should get a non-real number, which means, there we go. You can see it. Maths error. Okay. So this is very important. Any negative number under a even root, you will get a non-real number. Let's look at this one. We have here the fourth root. Remember, 4 is even. So this is a even root. So if we go to our calculator again, all right, let's just quickly go there, shift, and say there. Then we put the 4. You see the 4 there? And then inside, let's put in the -7. What do we get? Maths error. Do you see that, guys? Do you see that? So this is, again, the even root of a negative number leads us to a non-real number. Then let's look at this one. The sixth root. So the 6 here, okay, remember, this is the sixth root. Okay, this is another even root, but it's a negative number that's inside the root. So we should get what we refer to as a non-real number. So let's go again. Say shift, and then we go and press here so that we can access this option, which will allow us to punch in the number 6, and then let's put in the -5. What do we get? Maths error. Do you see that, guys? So these here are non-real numbers. Let's repeat. Not all numbers are real numbers. The even root of any negative number is what? Is called non-real or imaginary. Are we together, guys? So for example, like I said, the square root of -1, that will give us a non-real number. The square root of -28, that will give us a non-real number. The fourth root of -7, that will give us a non-real number. The sixth root of -5, that will give us a non-real number. So in other words, what I'm saying is any even root. If it's even, guys, if the root is even and there's a negative number inside, then you know it's non-real. Maybe someone is sitting there and they're asking themselves, what about the odd negative number? What about the odd root, Menier? Okay, that's a different story, guys. Okay, so for instance, look at this. This is grade 10, guys. The cube root of -27. The cube root of -27. Different story. This here will not give me a non-real number. This will actually give me a number. So let's go here. So if it's an odd root, it's a different story. Let's say shift 3, -27. You see? So here I actually get a real number. Okay? And maybe someone will ask, what kind of real number is this? All right? All right? And I know the kind of real number it is, it's a rational number. But what kind of rational number is it? Is it an integer? Definitely qualifies as an integer. Is it a whole number? No, it doesn't qualify as a whole number, because remember, whole numbers start at 1. They start at 0, increase by 1 up until infinity. So it's not a whole number. Is it a natural number? No, it's not a natural number, because natural numbers start at 1 and increase by 1 up until infinity. Lebutwala, do I offer lessons for grade 8? Yes, I do. I'll be having a grade 8 session for term 1, 2025 at 9 a.m. today. So yes, I do offer for grade 8. I offer for grade 9. I'm going to be having a session for grade 9 later on in the evening. Please go to my channel on the homepage. You'll see the schedule for today, which is Monday, what I'll be actually covering for the content for the respective grades, grade 8, 9, 10, and 11. Okay, so rational. So currently I'm doing grade 10, guys. Those who are joining in, this is grade 10. So this is very important, okay? The odd root of any negative number will not be non-real, okay? It's only the even root of any negative number that will give me a non-real or imaginary number. So hopefully that's clear for all of us. I'm going to move on, guys. I'm going to move on. because we don't have that much time left. Okay, now let's look at what a rational number is. Remember, the symbol for rational number was the Q, that's a standalone. What is the definition of a rational number? Guys, this definition needs to be hammered into your mind and your heart. Okay, so what is a rational number? So simply put, a rational number, which has the symbol Q, is any number which can be written as, now this here, A over B. In other words, which can be written as a fraction. A rational number is a number, I repeat, a rational number is any number which can be written as A over B. In other words, it can be written as a fraction. As a fraction. I repeat, it can be written as a fraction. Now we need to take note of something about this fraction. This fraction, it's where A, in other words, where the numerator value, which is A, which is at the top, where A and B are what? Are integers. So both A and B in your fraction need to be integers in order for it to qualify as rational. Your numerator needs to be an integer. Remember, what are integers? Let's recap. Integers are positive and negative whole numbers. And remember, we actually talked about the family of integers, that they range from negative infinity, there's no beginning, up until positive infinity, there's no end. But they increase and decrease by 1, okay, which is very important. So our A and B, the numerator value for rational numbers and the denominator value for rational numbers, need to be integers in order for them to qualify as a rational number. So I repeat, a rational number is any number which can be written as A over B. In other words, a fraction, where A, the numerator, and B, the denominator, are what? Are integers. And what? And B, which is very important, meaning the denominator, can never, ever be 0. Lebotwala, you can send me a private message. If you need private lessons and not group lessons like I'm doing right now, you can send me a private message on TikTok and I'll basically follow up with you personally so that we can arrange that. Where B cannot be 0. Okay, so this is very important. I'm going to repeat, a rational number, Q, is any number which can be written as a fraction, where A, meaning the numerator, and B, meaning the denominator, are what? Are integers. And B, meaning the denominator, can never be 0. Now maybe someone in the comment section can let me know, why can't B ever be 0? This is something you guys should know from grade 9. Why can't my B be 0? Meaning the denominator. Why can't I have B or the denominator being 0? Can anyone answer me that question in the comment section? Landi, where you are amazing. You are amazing. It will be undefined. Landi, where is absolutely spot on. You. Alright, guys, the denominator cannot be 0 because if it is 0, then it's no longer a rational number. As Landiwa said, if we have the denominator as 0, then the fraction is undefined. The number is undefined. Okay, so that's very important. B can never be 0. B can be any integer except 0. A, on the other hand, can be any integer. All right. It can also be 0, it doesn't matter. But the denominator, guys, we can never have the denominator be 0. Okay, so Landiwe is spot on. Now, here are examples of rational numbers. Look at the fraction, the numerator, 10. Is this an integer? Yes. Denominator is 1. Is this an integer? Yes. Is this 0? No. So this is a rational number. Why? Because it fits the definition. A rational number is any number which can be written as a fraction, where A, the numerator, and B, the denominator, are what? Are integers. But B can never be 0. Please, people, never. So 10 over 1, rational number. Spot on. 21 over 7, is this a rational number? Let's check. Is the numerator an integer? Yes. Is 7 an integer? Yes. Is 7 0? No. So therefore this is a rational number. Minus 1 over minus 3. Is minus 1 an integer? Or is negative 1 an integer? Yes. Is negative 3 an integer? Yes. Is negative 3 0? No. So therefore this is a rational number. Negative 3 over 6. Is negative 3 an integer? Yes. Is 6 an integer? Yes. Is 6 0? No. Is this a rational number? Yes. So this is a rational number as well. So this is how we distinguish what a rational number is. A rational number, I repeat, with the symbol Q, is any number which can be written as a fraction. In other words, the numerator and the denominator need to both be integers, but the denominator can never be 0. Enlita Kumkwebo, you're asking what is the difference between an integer and a whole number. Maybe I can ask someone in the comment section to answer you so that I can check if people have been answering. Guys, what is the difference between an integer and a whole number? What did we say a whole number is? I want someone to comment in the comment section so I can see if people have been listening. What is a whole number and what makes it different from integers? I'm gonna wait. Before I continue on, I'm gonna wait for someone to answer. So I've just made the screen blank a little bit so that I can have people answering the question. Whilst people are answering, whilst people are typing, let me just do the following, just to repost the schedule so that people can know what is happening for today, just so that people know what's happening for today as I await. For today, so yeah. Pixie just answered an integer is a positive and negative whole number and it increases or decreases by 1. Very good, Pixie. Very good. An integer is a positive and negative whole number. All right. Yes, very, very good. Thank you so much, Pixie. That is okay. So integer is both negative and positive whole numbers. Starts from positive, includes negatives. Very good. Landi, where integer includes positive and negative numbers, and whole numbers start at 0 and they both increase by 1. Very good. I think Landi has also just summarized it very nicely. Look at Landi's definition. Integer includes positive and negative numbers. All right. Whole numbers, on the other hand, they start at 0. Okay. Okay. So whole numbers start at 0, increase by 1. Okay. So if you're looking at the family of whole numbers, you're looking at 0, 1, 2, 3, 4, and so it goes. But if you're looking at the family of integers, you have the whole numbers included in there, but you also include together with the whole numbers, because whole numbers are 0, 1, 2, 3. But all of a sudden with integers, you're going to also extend your family of whole numbers and include negative numbers. Negative 1, negative 2, negative 3, negative 4, and so it goes. So integers include negative whole numbers. Does that make sense? So hopefully that answers the question. Guys, I'm very happy. It means you guys are listening very, very well. And Litam Koiba, I hope you are good. Thank you so much. Now I know integers can be negative, then whole numbers are not negative. Very good. Okay, whole numbers start at 0. Okay, they increase in the positive direction and include positive numbers 1, 2, 3. But then integers, it's both positive and negative whole numbers. So thank you so much, guys. I really love this. You guys are I love it. I love it. I love it for you guys. I love it for you guys. Now, this is the kind of positivity that I want in this live session. If we can start it off like this, guys, we, we're gonna massacre the Mets next year. We're gonna kill it. Oh man, I love it. Thank you so much. I really appreciate you guys' answers. Pixie, thank you so much. Margaret, thank you so much. Lita Mkwebu, thank you so much. Owane, thank you so much. Landiwe, thank you so much. Kotoi, thank you so much. You guys are phenomenal. Keep it up. Keep it up. Keep it up. Keep it up. All right, let's go. Let's move. Let's move. Let's move. Sorry, let me just get this schedule. So please, for those who are joining in, 7 o'clock, we are currently busy with the grade 10 session. At 9, we'll be doing the grade 8 session on whole numbers. At 9 p.m. tonight, we'll be doing grade 9 whole numbers, and then at 7 p.m. we'll be doing grade 9, and then at 9 p.m. later on today, we'll be doing grade 11s. Okay. Okay, let's go. Sorry, let me just take this out. Thank you so much. That was just from you guys to answer, and I just wanted to sort of get the schedule. Okay, let's move. So we've just looked at examples of rational numbers: 10 over 1, 21 over 7, minus 1 over minus 3, and negative 3 over 6. So in all cases, numerators and denominators are integers. So that's something to note. For rational numbers, or in all cases, the numerator and the denominator will always be integers. Okay, please take note of that. Now here's the thing. All integers are rational numbers because they can all be written with a denominator 1. What do we mean by this? If I write negative 6 is an integer. We all know that, right? But negative 6 can be written as negative 6 over 1. Hopefully you guys know, you all know that. That is why they're saying all integers are rational numbers. Remember, rational numbers are fractions, but the fraction, the numerator and the denominator need to both be integers. So hence negative 6 can be written as negative 6 over 1, which is rational. 0 can be written as 0 over 1, which is also a rational number. That's why we're saying these integers are actually also called rational numbers. All integers, not some integers, all integers are what? Are rational numbers because they can all be written with a denominator 1. I hope you guys know that. All integers, 7, for instance, the number 7 can be written as 7 over 1. The number 12,000 can be written as 12,000 over 1. Okay, so basically that's why we are saying all integers are what? Are rational numbers. Why? Because they can all be written with a denominator 1. Hopefully that makes sense. Okay, so that is basically, in summary, what a rational number is. A rational number, the symbol Q, is any number which can be written as a fraction. Okay, where A, meaning the numerator, and B are integers, and B cannot be 0. KTG stands, you can ask your question in the comment section. Go ahead. Okay, maybe I can allow you to answer your question before I move on, because I want to move on to the next thing, which is irrational numbers. Okay, so just as you get your question sorted, remember we said that in the real number system, we can divide our real number system into rational and irrational numbers. And remember, rational numbers include integers, whole numbers, natural numbers. Okay, so this space here is for rational numbers. Okay, but then we have integers, which are part of rational numbers, whole numbers, which are actually rational numbers, but they are also integers. Then we have natural numbers, which are actually rational, they are integers, they are whole numbers, they are natural numbers. Okay, can there be a number without a denominator like these ones? Can there be a number without a denominator? Remember, guys, all numbers can actually have a denominator. So for instance, like I said, -6 can be written as -6 over 1. Any number can be written as that number over 1. Okay, so hopefully that makes sense. Okay, hence I'm saying, for instance, 0 can be written as 0 over 1. 7 can be written as 7 over 1. Okay, 12,000 can be written as 12,000 over 1. Okay, so if you're asking, can there be a number without a denominator? If it's a real number, it will always have a denominator. Okay, so that's very important to note. Okay, let's move on, guys. Irrational numbers. What are irrational numbers? Yes, we're going here. We're going there now. Irrational. In other words, they are not rational. Let's look at what not rational numbers are. So you are asking Landiwe, in thought you are in the right direction. We are getting into that now. Now, what are irrational numbers? These are numbers, okay? These are numbers that cannot be written as a fraction with the numerator and denominator as integers. Now, this is the important part here. Remember that when we looked at rational numbers, these are numbers that can be written as a fraction where, and this goes together, it has to be written as a fraction where the numerator and the denominator are integers. Now, all of a sudden, when we look at irrational numbers, we are saying these are numbers that cannot be written as a fraction where the numerator and the denominator are integers. Okay, so in this case, we'll look at the number and we'll be like, oh, okay, the number cannot be written as a fraction where there's a condition. The fraction does not have an integer in the numerator and an integer in the denominator. Okay, so those are irrational numbers. These are numbers that cannot be written as a fraction with the numerator and denominator as integers. So let's look at some examples, because here we've got some examples. If you look at this, the square root of 2, okay, the square root of 2, if I was to write this as a fraction, it would be the square root of 2 over 1. I hope you guys are with me here. So yes, the square root of 2 can be written as a fraction. The square root of 2 can be written as the square root of 2 over 1. But let's check. Is this fraction rational? Look at the numerator. Is the numerator an integer? Is the square root of 2 an integer? No, it isn't. Okay? Square root of 2 is not an integer. Is the denominator an integer? Yes. Remember that in order for this number to qualify as rational, okay, it has to be that the numerator, a, and the denominator, b, are both integers. Okay, it has to be that they are both integers. We can't have one being an integer and the other one not. So let's look at this. The square root of 2, is the numerator an integer? No, it isn't. Is the denominator an integer? Yes, it is. So the square root of 2 over 1, is it a rational number? No, it is the opposite of a rational number. It is irrational. Irrational. All right. So these are numbers that cannot be written as a fraction with the numerator and denominator as integers. Both need to be integers, all right, in order for them to qualify as rational. But in this case, what are we seeing? The numerator is not an integer. The denominator is an integer. Is this rational? No, it's not. It is irrational. Irrational. Okay, let's look at the next number. Square root of 3. Square root of 3 over 1. That would be how we would write it as a fraction. Is the numerator an integer? No. Is the denominator an integer? Yes. Is this a rational number? No. Why? Because the numerator is irrational. Okay, it's not an integer. Thank you so much, Leo Styles, for the TikToks. And then the denominator is 1. So basically that means that this is irrational. It's not rational. If it was rational, both of these would be integers. Does that make sense? Okay, so if we have one of the numbers being an integer, it does not qualify this as a rational number. Let's move on. Look at this. The cube root of 4. Okay, this is the cube root of 4. The cube root of 4 can be written as the cube root of 4 over 1. Okay. Is this a rational number? No, it isn't as well. Why? Because the numerator, is it an integer? No, it isn't. Is the denominator an integer? Yes, it is. Is this rational? No, it isn't. It is irrational. Okay. Let's look at this symbol here. Does anyone know what this symbol stands for? Should have been exposed to it in grade 9 a little bit. Yes, Mkwebu, it is pi. just with this guy, it's not pi as in pi, P-I-E, because if it's pi with P-I-E, it means you are eating a pie. All right, this is the symbol pi. Okay, and you guys actually were exposed to the approximation of pi. All right. Okay, it's Jess. I know it is vacation, but I guess if you were here at the beginning of the video, then you would understand why we're doing this. Okay, and just allow those who want to be here, and you can actually, yeah, don't harass yourself by being here. So pi, all right, is a very, very important irrational number that we have, and I'm going to actually look at it in the calculator so that you can understand. I'm going to extend the definition of both rational and irrational numbers when we look at the decimals of each of these numbers. Okay, so just hang tight. But for now, pi is something that you need to know, is that pi is irrational. So you guys learned about the approximation or the estimate value of pi, which is 3,14. This 3,14 is not actually pi. It is an estimation. It is an approximation. It is a value that is close to what pi is. And it is not, 3,14 is actually rational. It is not irrational. Pi, on the other hand, is an irrational number. But this approximation of pi, 3,14, is not irrational. It is rational. Okay, and I will explain that when I look at the decimals of each of these numbers. Okay, so just hang tight, Joanna, you will get the clarity that you need. Okay, so you will get the clarity. Great and really. Then let's look at this one. 1 plus root 5 over 2. Rational or irrational? Look at the numerator. 1 plus, there's the there's the square root of 5. So this here, right? The minute we have something that has a even root and it's a number that's positive, then you know the numerator is basically not an integer. The denominator, on the other hand, is an integer. Is this rational? No, it's not. It is irrational. Okay. All right. Sorry, guys. I just want to close the door. Yeah. Okay. All right. So let's go. So the conclusion then we can make about the square root of 2, the square root of 3, the cube root of 4, pi 1 plus root 5 over 2 is the following. These are not rational numbers. Why? Why are they not? Because and this is the very important point here, the numerator and denominator is not an integer. Okay, remember that in order for these to qualify as rational numbers, both the numerator and the denominator need to be integers. But we are finding that one of them does not qualify as integers, and that is why we disqualify them as rational numbers and we call them irrational. Irrational, all right? So they don't qualify as rational numbers because the numerator and the denominator are not both integers. In order for them to be rational numbers, the numerator and the denominator need to be both integers. Okay, let's move on. So those are irrational numbers. Now I want to go into the decimals, because once we understand the decimals of both rational and irrational numbers, then the case is closed, all right? And I need you guys to really listen to this and listen to this very well, because I feel that this then basically helps us in any situation to determine whether a number is rational or irrational using our calculator. So, and I'm going to go back to all these values that we had before so that you can appreciate the decimal values that you get for rational and irrational numbers. Okay, so let's look at this. Decimal numbers. Now, decimal numbers, people, I hope you guys know what decimal numbers. You guys did decimal numbers in grade 9, you did it in grade 8, you did it in grade 7. So by now you should be well equipped with what decimals are. Now, all integers and fractions with integer numerators and non-zero integer denominators are rational numbers. I'm going to repeat this. All integers, this is something you should already know, all integers and what? And fractions. Fractions with what? With integer numerators. You have integers in the numerators of these fractions and non-zero. This is very important. What do we mean by non-zero? It means that numbers that are not zero. Okay, the word non means not. It's a prefix. Okay, not zero. So we are saying all fractions with integer numerators, meaning the numerator is an integer, and non-zero integer denominators. As long as the denominator is not zero, we refer to these as rational numbers. I hope we are together here. Together, people? One more time. All integers. We know that all integers are rational numbers, right? Okay, we looked at examples. -6, integer, but you can be written as -6 over 1. 0 can be written as 0 over 1. 7 is 7 over 1. These are all integers. All integers and fractions with integers. So these fractions with integers in the numerator and non-zero integer denominator. In other words, the denominator is not a 0, but it's an integer. Are what? Are rational numbers. Okay, so very, very important. I think that's a beautiful summary statement. Let's continue. Remember, when a denominator of a fraction is 0, when the denominator of a fraction is 0, then the fraction is undefined. Yes, I am, Jose. I am. When a denominator of a fraction is 0, then the fraction is undefined. Very important. Okay, I think Landi helped us to understand that earlier on today, and she answered that question very well. Now listen to this. You can write any rational number as a decimal. You can write any rational number as a decimal number, but not all decimal numbers are rational numbers. Grade 10, Dollface. I repeat, you can write any, grade 10, Celebe. You can write any rational number as a decimal number. But not all decimal numbers are rational numbers. Okay. Now let's look at the specifics and details. Now you are going to understand the difference between rational and irrational numbers as far as their decimals are concerned. Okay? But this is important. You can write any rational number as a decimal number, but not all decimal numbers are rational numbers. Okay? Very important question. Is 3,0 a rational number? We are going to answer that question now, Landio. Check this out. Now, under rational decimals, okay, under rational decimals, Yasura, my son is going to grade 9 next year. How do I motivate him in maths? Well, if you want to motivate him in maths, you can have him join my live sessions. I will help you in helping him to be motivated. Okay, I'll be having a session later on for grade 9s at 7 p.m. So here we go. 1. Rational decimals. 1. Rational decimals are terminating decimals. Have you guys watched the movie Terminator? Yeah, okay. So anyways, the word terminate means to end. Terminating decimals. Okay. It's when decimals end. Okay. So here we are. We've got a fraction here. It's 4/10. 4/10 can be written as a decimal. And the easy way to do this, guys, okay, you guys know that 4/10 is a rational number because the numerator is an integer, the denominator is an integer. So here we are. All you do is you say 4/10. Okay, did you see what I did? I just pressed that button. You put in the 4/10, and then you come here to this button, which is you change the fraction into a decimal. So you press SD, all right, equal, you get 2/5, sorry, you first press 2 equal. What this does, it actually simplifies the fraction for you. 4/10 is actually written as 2/5, and then you go and press SD. And what that does, it changes the fraction into a decimal. But what do you notice? This is 0,4. After the comma, the 4, there is no more numbers after the 4. In other words, the decimal terminates. In other words, stops, ends. So all terminating decimals are referred to as rational numbers. Whenever a number or the number after the comma stops, we refer to that as terminating decimals. So rational decimals terminate. Okay. So earlier on, Landiwe asked, is 4 or is it 3,0? You said 3,0. I think Landiwe asked, is 3,0 a rational number? Okay. And simply put 3,0 after the comma, it stops. So this is terminating. So that qualifies as a rational number. Okay. 3,14. There's no continuation of the decimal. In other words, after the comma, the numbers stop, they terminate. So this is also a rational number. So all terminating decimals are referred to as rational numbers. Okay, very important. So that's the first thing about rational numbers. If you look at their decimals, they terminate. In other words, the numbers after the comma, they don't go on forever. They actually stop at some point. Whether that be 0,1, 2, 3, 5, 8, and it stops, there's no continuation, this is also called a terminating decimal. Okay? Because at some point the number stops. There's no continuation of numbers after this particular number, which is very important. So terminating decimals, just remember the word terminate means to come to a stop or an end. Okay, so terminating decimals come to an end, they stop. Okay, terminating decimals or are rational. Let's move on to recurring decimals. Another type of decimal number that we get is when numbers repeat after the comma. Terminating decimals. These are decimal numbers that have a repeating single digit. Well, it can be a repeating single digit, or sometimes it can be multiple digits repeating. But something to note is that recurring decimals are decimal numbers that have a repeating single digit. So for example, 1/3. Let's just go to our calculator very quickly. If you say 1/3. Now guys, we know that 1/3, right, is a rational number. Why? Because the numerator is an integer, the denominator is also an integer. So if we go ahead and say equal, then we go and press this button SD, what do you notice about the decimal? 0, look at this. 3. Okay, this goes on infinitely. Why do we know that this goes on forever? It's because our calculator space, it's just that our calculator space is limited to this. But 3 is actually recurring, it repeats. Okay, so recurring decimals are the second type of decimal that qualify as rational decimals or rational numbers. Okay, then something to note, whenever a number repeats, we usually put a dot which indicates that 3 repeats, or we can put a line to indicate that the 3 repeats. So if you see this, guys, this is just meaning 3 repeats. Okay, so this is 0,3333 infinitely. This here as well is 0,333, meaning 33333 infinitely, no end, goes on forever, repeats infinitely. Okay. So the dot or the bar notations both mean single digit, 3 repeats. That's a recurring decimal. Look at this point. Recurring decimals that have a recurring pattern of multiple digits. Sometimes it's not just one number that repeats after the comma, but sometimes it's multiple numbers that repeats. Okay. For example, 2/11 can be written as 0,18181818 infinitely. So look at this. This bar is written over 18 to indicate that 18 repeats. 18181818181818. Recurring pattern of 1 and 8. So if you look at rational numbers, there are 2 types of decimals when it comes to rational numbers. You can either have terminating decimals, like 4/10, which is not 4, because the 4 stops, doesn't repeat, doesn't continue, it stops. Or recurring decimals, repetition of either single digits, or it can be multiple digits. Okay, single digits like 1/3 when you get 0,33333, right? Like we did, or like we got here. Or if you look at this one, multiple digits, 2/11. If we press equal and then press SG, look at this, 18181818 repeats infinitely. Okay. And remember, what did we say? A dot on top of the number, a shaded one, or a bar on top of the number indicates repetition. So I hope that makes sense. Okay. So hopefully that is clear. Rational numbers, you can notice rational numbers by the terminating decimal or the recurring decimal. Terminating decimals are rational numbers. Recurring decimals of single digits are rational numbers. Recurring decimals that have multiple digits that are recurring after the comma, they are also rational numbers. So here's a concluding statement here before we close. If you are asked to identify whether a number is rational or irrational, first write the number in decimal form. Your calculator can always help you with that. If the number terminates, it is rational. Okay? If it goes on forever, then look for a repeated pattern of digits. If no repeated pattern of digits is seen, then the number is irrational. Okay, I'm going to repeat this. If you are asked to identify whether a number is rational or irrational, first write the number in decimal form. If the number terminates, it is rational. If it goes on forever, then look for a repeated pattern of digits. Because you'll know if there's a repeated pattern of digits, then it's rational. If no repeated pattern of digits is available, then the number is irrational. So those are things you need to take note of whenever you are doing, if wanting to identify the difference between rational and irrational numbers. Okay, so guys, that basically brings us to that end. Okay, so hopefully we actually now have a clear understanding of these types of numbers. I just want to show you quickly with irrational numbers, because remember I wrote down these irrational numbers earlier on, and I just want to show you the difference between these irrational numbers when it comes to their decimal. So let's look at the square root of 2, for instance, the square root of 2. So if I type in the square root of 2, then after that I press equal. There's the square root of 2. Then I press SD. Do you see the decimal makeup after the comma? This is 41421356 and the thing is, this would go on infinitely. After this comma, it would go on infinitely, but then the thing is, the calculator does not have enough space. But what do you notice? One, is there a repetition? This goes on forever, but is there a repetition of numbers? No, there isn't. So does this qualify as rational? Okay, there's no recurring decimal. Okay, and there's no termination. In other words, there's no stop. Okay, now how do we know that there is no stop? Okay, you can see 41421356. The calculator has no space, so basically if there was more space, you'd see more numbers and it would go on infinitely, but there's no repetition. So this then qualifies as irrational. Do we know? So we don't know the repetition of 4. Remember, KTG stands, in order for it to be rational, the repetition needs to be continuous, all right? The pattern, there has to be a pattern of repetition. So if you look at this one, 4142, is this a repetition? Is there a pattern of repetition? No, there is no pattern of repetition. No, it's grade 10, guys, it's not grade 8. Okay, but this obviously you do as well in grade 9 and you do it in grade 8, okay? But this is just revision of grade 9 work and grade 8 work for the grade 10s, okay? So no repetition, guys, no repetition, okay? That basically means that, okay? OGGM, we've been doing real numbers. What do you mean, can we do real numbers now? We've been doing that now. We've been doing it at this present moment. That's what we've been doing, okay? Yeah, so that's what it is, that repetition. That repetition is not here. There's no pattern of repetition, okay? So that's very important. No pattern of repetition simply means that, okay? Look at the schedule on the home page, people. Some of you are asking me questions about grade 11, grade this, grade that. Go onto the home page. The most recent video I posted was basically outlining the schedule. Okay. So please, people, no repetition. Okay, so there's no repetition. That basically means no repetition of pattern means that this is irrational. Okay, that's the square root of 2. That's why the square root of 2 qualifies as an irrational number. So when you are lost, always go to your calculator. Okay, look at the square root of 3. So the square root of 3 equal, let's press SD. Let's just check the denominator. Look at the decimals. Look at this. 1,732050808. There is no pattern of repetition after the decimal. Very important. Look at the 7320508. So basically, no repetition, no recurring, no termination. This means that this is irrational. Okay, very important, guys. Very, very important. This that we are doing here. And then let's look at one more. Oh, pi. If you go to shift, if you press shift and then you go to this symbol here, here's the symbol of pi there. You see that? So you press shift. Shift allows you to select all the yellow things in your calculator. So you go to this button, times 10 to the power x, and then look at this, the symbol of pi. If you press equal, there's pi there, and then you press SD. Look at this. So this here is 3,141592654. Repetition after the decimal, infinite repetition, no way, Jose. There's no repeated pattern of numbers. So therefore we call this a irrational number. Okay. People, this is basically how, okay, you can clearly see that after this 4, there would be more numbers. But the thing is, there's no space because our calculator is limited. If we had a calculator that was much bigger, you'd see more numbers. But there would be no pattern. No pattern of repetition means that this is an irrational number. So hence I'm saying pi is irrational. But what you guys used as an estimation in grade 9, 3,14, this is not irrational. This is a rational number. It's an approximation. It's an estimation of the value of pi. So the estimation of the value of pi is actually not irrational. It's rational. Why? Because 3,14 qualifies as a terminating decimal. Okay, whereas pi in and of itself is actually irrational, okay, which is very important. Okay, hopefully that makes sense. Yes, 22/7 is also an approximation, people, right? It's an approximation of the pi value. It is not pi, okay, because look, 22/7, if you press SD, yeah, so it's the approximation. Very important, very, very important, okay? Very, very important. Okay, so guys, I'm actually gonna hold it right there. Hold our horses right there. Okay, because typically, if we're talking about 22/7, right? Remember that 22/7 is actually rational, right? Because remember, 22 is in the numerator, 22 is a, what is 22? Okay, I just wanna tell you something. The difference between 22/7 and the actual value of pi. Okay, remember 22, the numerator value is actually an integer, and then 7 is also an integer. So if we press SD, something that I want you to note is that this 3,1428571. Okay, here's the thing. 14. You see this 2? Do you see this 8? What happens to this 8? This 8, what would it do to the 2? If we were to round off, we'd round it off as 3,143. Okay, that would be the round off if we were to write it as 3,143. Now, here's the thing. The last digit here is actually rounded off. Okay, so this is 3,142,857. This is where it would cut. So it would be 3,142,857. Then it would repeat itself. 142,857. 7. 142,857. This would basically be the value of 22 over 7 if we were to write it down in the calculator. This 142,857, this here would repeat. This entire digit would repeat. 142,857, 142,857, 142,857 for 22 over 7. So this is also an approximation, guys. 22 over 7 is the approximation of pi. Okay, so that's something that I hope will be clear for all of you. But it's just that your calculator, what it does is that because we don't have more space, it rounds off the last value. That's what it does. Your calculator does that. It rounds it off. So 2, obviously the 8 would say to the 2, we go up. So that's why you have 143. But what I want to say is that 22 over 7 written as a decimal, this 142,857 repeats 142,857, 142,857 for 22 over 7, because 22 over 7 is actually rational, and that is a recurring decimal of multiple digits. Okay, so I hope we are clear about that. Yeah. So what I want you guys to do now as I close and conclude. Alright, so guys, grade 10, same time, tomorrow, same place. We'll continue on, but I want to leave you, and I'm going to actually take a photo of this. I'm going to post the following exercises so that you guys can actually do this. Just wait, hang on, hang tight. I just want to... I want you guys to actually go ahead and do this, right? This here says state whether the following numbers are rational, irrational, or neither. All right. So for A, for instance, you're going to state whether this is rational or irrational. Maybe very quickly before you guys leave, I want you guys to let me know, A, is this 0.25? Is it rational or irrational, or it's not both? 0.25. Okay, Elita says rational, Towana says rational, Landio says rational. Okay, that means we've got the understanding down. Why do we say it's rational? Is it terminating? Is it recurring? What is it? 0.25. Why do we say it's rational? Because we need to understand why we are saying it's rational. What type of decimal is this? Very good, Elita. So it's terminating. So all of us get the point. Beautiful. Okay, this one. Next one. -2. Rational or irrational? Okay, rational. Okay, so KTG stands, please understand -2 can be written as a fraction and -2 over 1. Remember that, okay? So -2 is definitely rational, okay? Okay, next one. What about pi plus 6? Yes, Landy, it can be written as a fraction. Landy, very good. Irrational. OG, very good. Ria, very good. Irrational. Very good, guys. Okay, then last but not least, rational or irrational or neither? Negative, the square root of -16. The reason why that number, pi plus 6, is irrational was because of square root of -16. Is it rational, irrational, or neither? Meaning not both. Square root of -16. That's the even root of a negative number, Elita. Is it rational, irrational, or neither? No, Elita, it's not irrational. Okay, the options you have: rational, irrational, or neither. Remember, guys, it's neither. Okay, this does not qualify as a rational number, it does not qualify as an irrational number, it qualifies as non-real. Non-real. It's not real, it's non-real. It's not a real number, it's a non-real number or imaginary number. Okay, guys, thank you so much. What I'm gonna do, this example, these exercises, I'm gonna post a slideshow of the exercises that I want you guys to do, just so that you can actually check yourself and check if you actually have got this identification of different types of numbers down. So I'm gonna take after I leave the live just now, in 5-10 minutes, I'm gonna post a exercise video just on my TikTok page so that you guys can go over that. Please do it, and then tomorrow before we join or start the session, I'm actually going to check what our answers were for that exercise. But thank you so much, it was good. Thank you for joining. Tomorrow, guys, same time. So basically the grade 10s, 7 a.m. We have 7 a.m. sessions. I know it's early, but that will help me distinguish between those who are serious and who are not. So grade 10 maths, 7 a.m. tomorrow morning, same time, same place. Grade 10 maths, 7 a.m. tomorrow morning. We'll continue from where we left off. And those other grades, please go and check my schedule on the page, the home page. My recent video basically outlines what the schedule is for all the other grades.